Electrochemistry is the branch of chemistry concerned with the internal relation of electrical and chemical changes that are caused by the passage of current. The importance of electrochemistry is undeniable. We literally can live without electrochemistry for purposes of function and transmission of signals through the nervous system. Electrochemistry is also vital in a wide range of important technology applications. For example, batteries are important not only in storing energy for mobile devices and vehicles, but also for load-level energy enable the use of renewable energy conversion technologies. An electrochemical cell is a device capable of either generating electrical energy from chemical reactions or using electrical energy to cause chemical reactions. The electrochemical cells which generate an electric current are called voltaic cells or galvanic cells, and those that generate chemical reactions via electrolysis, for example, are called electrolytic. A galvanic cell converts chemical energy into electrical energy. An electrolytic cell converts electrical energy into chemical energy. Oxidation takes place at the anode and reduction takes place at the cathode. In an electrochemical process, electrons flow from one chemical substance to another, driven by an oxidation-reduction-redox reaction. A redox reaction occurs when electrons are transferred from a substance that's oxidized to one that's being reduced. The reductant is the substance that loses electrons and is oxidized in the process. The oxidant is the species that gains electrons and is reduced in the process. The associated potential energy is determined by the potential difference between the valence electrons in atoms of different elements. We use two different half cells to measure how readily electrons can flow from one electrode to another, and the device used for measurement is called the voltmeter. The voltmeter measures the cell potential denoted by E cell, which is the potential difference between two half cells. The Salter bridge allows the ions to flow from one half cell to another but prevents the flow of solutions. As indicated in the diagram, the anode is the electrode where oxidation occurs. Cu loses 2 electrons to form Cu2+. The cathode is the electrode where reduction occurs. Ag+ gains electron to become He. As a convenient substitution for the drawing, we use a cell diagram to show the parts of an electrochemical cell. For example, above, the cell diagram has oxidation, half cell, Salter bridge, half cell reduction. A galvanic cell induces a spontaneous redox reaction to create a flow of electrical charges or electricity. Non-rechargeable batteries are examples of galvanic cells. A reaction is spontaneous when the change in Gibbs energy is less than 0. Electrons flow from the anode, which is negative since electrons are built up here, to the cathode, which is positive since it's gaining electrons. An electrolytic cell is one kind of battery that requires an outside electrical source to drive the non-spontaneous redox reaction. Rechargeable batteries act as electrolytic cells when they are being recharged. A reaction is non-spontaneous when Gibbs energy is greater than 0. Must apply electrons to the cathode to drive the reduction, so cathode is negative. Must remove electrons from the anode to drive the oxidation, so anode is positive. Both galvanic and electrolytic cells contain 2 electrodes, the anode and the cathode. Cathode does not mean positive and anode does not mean negative. A voltmeter measures the electric current. In galvanic cells, this shows how much current is produced. In electrolytic cells, this shows how much current is charged in the system. Electrolyte, conducting medium, has contact with electrodes, usually in aqueous solution of ionic compounds. A Salter bridge joins the two halves of the electrochemical cell, filled with a salt solution or gel, keeps the solution separated, and completes the circuit. Cell notation or cell representation in chemistry is a shorthand method of expressing the reaction in an electrochemical cell. In cell notation, the two half cells are described by writing the formula of each individual chemical species involved in the redox reaction across the cell. With all the other common ions and inert substances being ignored, each species is separated by a vertical bar with the species in half cell grouped together, and the two half cells separated by 2 bars or slashes representing a Salter bridge, which generally contains an electrolyte solution such as potassium nitrate or sodium chloride that's left unwritten. It's common practice to represent the anode to the left of the double bar and the cathode to the right, and the aqueous species closest to the double bar. An electrolytic cell has 3 component parts, an electrolyte and 2 electrodes, a cathode and the anode. The electrolyte is usually a solution of water or other solvents in which ions are dissolved. Molten salts such as sodium chloride are also electrolytes. when driven by an external voltage applied to the electrodes. The ions in the electrolyte are attracted to an electrode with the opposite charge, where charge and transfer reactions can take place. Only with an external electrical potential of correct polarity and sufficient magnitude can an electrolyte cell decompose a normally stable or inert chemical compound into solution. The electrical energy provided can produce a chemical reaction which will not occur spontaneously otherwise. To illustrate the basic principles of a galvanic cell, let's consider the reaction of metallic zinc with cupric ion to give copper metal and zinc ion. The Band's chemical equation is as follows. We can cause this reaction to occur by inserting a zinc rod into an aqueous solution of copper 2 sulfate. As the reaction proceeds, the zinc rod dissolves and a mass of metallic copper forms. These changes occur spontaneously, but all the energy released is in the form of heat rather than in a form that can be used to do work. Construction of electrolytic cell. Two electrodes, cathode and anode, suspended in an electrolytic solution and connected to a battery. Anode is positive and cathode is negative. Oxidation takes place at anode and reduction takes place at cathode. Non-spontaneous reaction occurs. These may be irreversible. Flow of electrons from anode to cathode. Electrons leave the cell at anode and enter the cell at cathode. Now, as we can see here, the voltmeter reaches 0. In reality, the battery will start working in a minute, will stop after a short period of time. So, why this is happening? Because the battery is missing a very essential element, which is the solder bridge. Now, the solder bridge contains a gel of an ionic compound that reassures the neutrality of each compound. For example, the anode compartment is becoming more positive and the cathode compartment is becoming more negative. And the positive charge of the anode compartment will attract the electrons and therefore will prohibit the electrons from getting transferred to the cathode, and hence the role of the solder bridge. It will be pumping negative ions or anions to the anode compartment and positive ions or cations to the cathode compartment, and this way both compartments will remain neutral at all time. And this will help the battery to continue generating power until that it reaches equilibrium. Consider the following electrolytic cell where a ring is being plated with copper atoms. Now the copper electrode represents the anode where the oxidation is happening, and the ring represents the cathode where the reduction is happening. Both they're immersed in a copper 2 solution. As you can see in here, copper ions are being generated from the anode and they're being reduced at the cathode, which means plated on the surface of the ring. The copper electrode will decrease in mass with time and the ring will increase in mass with time. The presence of ions or gaining ions makes the solution darker in color, while absence or less ions in the solution makes the color faded.